In the previous video, we started talking about London dispersion forces, and we started talking about London dispersion forces as a form of intermolecular force. So a quick reminder for your intermolecular forces. Your intermolecular forces are what keeps molecules together, and that's what helps form liquids and solids. If we didn't have intermolecular forces, we would have no liquids or solids, since we need something to stick the molecules together, something like a glue between them. And those are what we call IMFs. And we saw that a way that IMFs can be formed is by taking advantage of the atom's electrons by themselves and the fact that they go around the nucleus, and sometimes they may line up on one side or another. And we can use this in order to form intermolecular forces because we know opposites attract, which means if I temporarily have a negative pole on this side and a positive pole on this side, and let's say this atom is in the neighborhood and is trying to form an IMF with this atom, it is possible that it could go this way, where it has its negative charge over here, positive charge over here, and it could form an IMF since positive and negative charges attract. It would be a temporary IMF because we know electrons will continue to move around the atom, but for that instant where this side of the atom has a positive charge and this side has a negative charge, they can connect and form an IMF. And we call this particular IMF a London dispersion force. And we said that all atoms and molecules have London dispersion forces because all atoms and molecules have electrons, and all you need are electrons in order to form these London dispersion forces. There are, however, some molecules where you can have more than just London dispersion forces. So there are some molecules where you can have more than one IMF possible. So they can have more than just London dispersion forces, and this happens if they are polar. We learned about polar and nonpolar molecules in the previous class. We learned that some molecules are nonpolar. So for example, this hydrogen is nonpolar because there's no change in electronegativity between either side. So the electrons are equally shared between the two hydrogens. But we also learned that hydrogen fluoride would be polar since fluorine has a higher electronegativity than hydrogen. So if fluorine has a higher electronegativity, it pulls the electrons closer to itself. So hydrogen fluoride is polar. Since hydrogen has a low electronegativity, fluorine has a high electronegativity, it pulls all the electrons towards itself, giving itself a partial negative charge. Now this is also a dipole in that it has two different poles, a positive and a negative side. But note how these two poles never flip. You're not going to have a time when hydrogen now takes the turn at being negative and fluorine becomes positive. Fluorine will always be your partially negative side because it has more electronegativity. So we call these permanent dipoles instead of temporary dipoles like London dispersion forces. So in London dispersion forces, we call them temporary dipoles because what we were looking at in London dispersion forces was that we got the negative or positive charge because the electrons were moving a certain way. And we said this is temporary because these electrons never stop moving, so they could move to the other side of the atom and flip the dipole. So this is a temporary dipole because temporarily the electrons are over here, but they could move somewhere else. This, on the other hand, is a permanent dipole because fluorine is always going to be more electronegative than hydrogen, which means fluorine is always going to attract electrons more strongly than hydrogen is. So if I have two hydrogen fluoride molecules, we know one end of hydrogen fluoride is always going to be negative, the other end is always going to be partially positive. So if I have a second molecule, the negative end of one molecule can attract the positive end of the other molecule because we know opposites attract. And in that case, the intermolecular force formed is called a dipole-dipole attraction. Why is it called dipole-dipole attraction? Because this is a dipole, this is a dipole. So I have two dipoles in my hand. They're both permanent dipoles, which means they're not going to flip their polarity. They're not suddenly going to switch their positive and negative sides. So I have two dipoles in my hand and they're attracted to each other. The opposite sides are attracted to each other, the negative attracted to the positive side. And so they're called dipole-dipole attraction. It's because it's between two dipoles that are permanent and they never flip their polarities. So some molecules can have both this dipole-dipole attraction, and these two still have London dispersion forces because guess what? hydrogen and fluorine still have electrons. And as long as something has electrons, it is capable of forming these temporary dipoles. So hydrogen fluoride doesn't just have dipole-dipole attraction, it also has a London dispersion force acting on it. We just tend to see the dipole-dipole more strongly because we can see the negative and positive charges that don't flip on either side of the molecule. So to conclude all of this, let's look at some practice. We'll take a look at certain molecules, and then we'll try to see what IMFs are present that would make them attract each other. So let's first start off with fluorine. We already saw this, but let's take a look at it again. So in fluorine, since I have two fluorines attached to each other, they're both equally electronegative. So this molecule is not polar. I don't have a positive side, I don't have a negative side. Overall, this molecule is neutral, it has no sides, but it's possible that temporarily the electrons come to one side of the fluorine molecule because electrons are constantly going around. If that should happen, then it could attract a different fluorine molecule where the electrons are on the other side. And since we have this temporary partial negative, so I'm not just going to say partial negative, I'm going to say temporary partial negative, and we have a temporary partial positive, it is possible to have this attraction. So what keeps fluorine molecules together? Anytime fluorine forms a liquid, it tends to be only London dispersion forces. Why only London dispersion forces? Because we have no permanent dipole. Both the fluorines have the same electronegativity, so the positive and negative ends could flip at any given point. So when we have temporary dipoles, which means the polarity can flip, we have only London dispersion forces. So because F2 is nonpolar, it cannot have dipole-dipole attraction. There's your shortcut. Anytime you see a molecule that's nonpolar, it's only going to have London dispersion forces. It is not capable of having dipole-dipole. That's why the previous lesson is important. The previous lesson was important because you learned how to tell the difference between something that's nonpolar versus something that's polar. And now you need to know what is polar and nonpolar so that you can figure out if it has only London dispersion forces or does it have both London dispersion and dipole-dipole. Let's take a look at a different example. Let's take a look at water now instead. So with water, we know we have oxygen attached to two hydrogens, and because of its shape, because it's bent like this, we know that oxygen being more electronegative is going to pull all of the electrons upwards. So because its shape is asymmetrical and we know oxygen is more electronegative than hydrogen, we know that the oxygen is going to grab all of the electrons towards itself, leaving hydrogen with a partial positive. And we know this won't flip. It will not flip because oxygen is always going to be more electronegative than hydrogen. So if I have two water molecules in the vicinity, the side of the water molecule that's partially positive, the hydrogen, is going to attract the side of the other water molecule that's partially negative, which is the oxygen. And this is going to create an intermolecular force. So if we look at water now instead, we see a slightly different story. Since water is polar, and think about why it's polar, it's because it's asymmetrical. One side is always going to be negative, one side is always going to be positive. Since it's polar, it's not just going to have London dispersion forces. Remember, anything that has electrons has London dispersion forces. Not only is it going to have London dispersion forces, in addition to that, it's going to have that dipole-dipole interaction since both the water molecules are dipoles. They have one side that's positive and one side that's definitely negative. All right, let's go ahead and look at a different molecule. Let's go ahead and look at methane, or CH4. So this is CH4. It's perfectly symmetrical, which means there's no side of this molecule that's negative and no side of this molecule that's positive. All of the electrons are evenly distributed around, except we know electrons are like planets. When they're moving around, they may by chance aggregate to one side or another. So if that should happen, let's say all of the electrons that are moving around CH4 suddenly aggregate over here, and there happens to be another molecule of CH4 where all of the electrons aggregate over here, what we have on our hands is a temporary partial negative charge over here and a temporary partial positive charge over here, and these two can attract themselves for a little while. As long as they exist, they can attract themselves. So if we look at CH4 methane and we look at what IMFs are present, we notice that it's only London dispersion forces because we're relying on those electrons moving like planets and aggregating to one side or another. And so since CH4 is nonpolar, it cannot have dipole-dipole, so it has to be London dispersion forces. All right, let's take the CH4 molecule and modify it slightly. So I took that CH4 molecule and made just one change to it. I replaced this hydrogen for a halogen, so something from group 17. So all I did was, instead of having CH4 now, I have CH3Cl, which means that instead of having all 4 hydrogens, I have 3 hydrogens and 1 chlorine. Now you can take a look at this molecule and definitely say it's a dipole, because we know that this end of the molecule is different from this end of the molecule. So this end is going to be positively charged and this end will always be negatively charged, because we know chlorine is more electronegative than hydrogen. So this end is always going to be negative, this end is always going to be positive, which means if I have another molecule just like it, these two will repel each other since they're positive, but these will attract each other since this is positive and this is negative. So with CH3Cl, because I have a negative on one side and a positive on another side and they don't flip around, we know this is a polar molecule. And so unlike CH4, which had only London dispersion forces, CH3Cl will have London dispersion forces since it has electrons and they're always going to be around the atom and could align on one side or another. So yes, it has London dispersion forces, but it also has the added bonus of a dipole-dipole attraction.